Hello, everybody, and welcome back to another Mr. Farney Earth Science video. In this video, we're going to be exploring the properties of the atmosphere, looking at temperature, air pressure, humidity, and then a couple other weather conditions that we can use to help us, infer what the different forecasts can be based on these specific conditions. Before we get too much into the conditions, we're going to learn a little bit about the technology and the terminology that are used in making these measurements. So we have various different types of weather instruments that scientists can use to collect weather data from Earth's surface. The first one that most people are aware of is the thermometer. We all know the thermometer. What does it do? It measures temperature. Another one that you might not be as familiar with is the one on the right here. This is called an anemometer. So we have thermometer, we have anemometer, and the anemometer, it measures wind speed. It has these little half bowl cup things on a spinny wheel, and you might have seen this before sometimes outside at different places, kind of like spinning around. What does it do is that it is able to convert how fast those little half bowl things are spinning into miles per hour or kilometers per hour wherever you are in the world. So it's a really cool tool to use to measure wind speed. Barometer, you might have seen this clock looking thing in my classroom at the front of the room. This measures air pressure. This allows us to know whether or not we have high pressure or low pressure, if we're going to have fair weather with high pressure, or if we're going to have not so fair weather with low pressure. We'll get more into the pressure differences in a little bit. A hygrometer, this measures humidity. This measures how humid the air is, how much moisture is in the air. This is one type of one where you hold in your hand, you spin it around, and it's able to gain the measurement of humidity by doing so. So using tools like these, we're able to identify 5 different properties of the atmosphere and learn a little bit about how they interact with one another. So the first thing, temperature, it's actually defined as the measure of average kinetic energy of the particles in a material, how fast these different air molecules are bumping around, moving around. We give them temperature association, if you will. Is there anything else on this slide? Oh, we have animations here. So temperature, it's a measure of heat. We give it a number, a specific number of temperature, whereas heat itself is thermal energy. It's the amount of energy associated with the movement of molecules or atoms. So if something has a high level of heat, that energy is going to be very high. Those molecules and atoms are going to move around very quickly, especially in the gaseous state. Temperature is kind of like the numeric representation of what's going on with that heat measurement. So temperature measures heat. And what is heat? It's how fast these different air molecules are moving around and bouncing around in the air. As we lose heat, it's going to become colder. As we gain heat, it's going to become warmer. We have various different scales of measurement that we can use to measure heat: Fahrenheit, Celsius, and Kelvin. And here are the various boiling points, freezing points, and then absolute zero. And absolute zero is the point in which all molecules stop completely moving. For our class, we're just going to focus on Fahrenheit and Celsius. That's the main two. And we're going to practice converting back and forth between Fahrenheit and Celsius a little bit with a little worksheet activity throughout this section. So at the bottom of the page here, or the slide, you'll notice here are the conversion factors from going from Fahrenheit to Celsius, and then Celsius back to Fahrenheit there. It's a plug and solve situation for both of these. The second property is air pressure. This is the amount of force that's exerted on a surface from the air above. So is there more on this? Here we go. As elevation increases, the pressure decreases. Might not know that kind of, or maybe if you've gone hiking or if you know anything about mountains, sometimes you'll hear people say the air gets thinner as you go higher through the atmosphere. And it's true, you lose a little bit of oxygen, but more specifically, the amount of force that is being pushed down as you go up, it's going to decrease because that density of oxygen or that density of air is going to decrease. So in this box here, it's very important. The general rule of thumb is colder air is more dense and it's going to sink. Warmer air is less dense and it's going to rise. And these are specific features that we've spoken about when dealing with convection and how it kind of drives movement in our atmosphere. With the cold air sinking, warm air rising, we can get these different types of circulation going on within our atmosphere. And air pressure, the differences in air pressure around the country, whether if we have a high pressure in one spot, low pressure in other, we start getting different types of movement from that. This one here, temperature inversion, we don't have to speak too much to. It's just this idea that in a normal situation, as you go from warm air at the ground and you go up in the atmosphere, it gets colder and colder. Temperature inversion is if we have some sort of warm layer of air kind of in the middle that's blocking that air from kind of like going all the way up into the atmosphere. And because of that block, we have this thermal inversion where cities are not actually able to radiate their heat and they stay cooler. Issue though with a thermal inversion is that it leads to fog, low-lying clouds, and then since that air is not able to kind of escape up, it can lead to air pollution. So temperature inversion, instead of a decrease in air temperature as we increase in elevation, we are increasing the temperature. Kind of similar to how the stratosphere works, where as you go up through the stratosphere, instead of the temperature decreasing, it's going to increase. So that's temperature inversion. And this is just another picture that kind of illustrates that point. Wind, what makes wind? Well, first off, the sun causes different areas of the earth to be heated at different temperatures. So we have a difference in temperature here, high temperature, cold temperature. Differences in air pressure cause that air to move. So let's think about this. Hot temperatures, cold temperatures, high pressure, low pressure, high density, low density. It kind of reminds me a little bit about convection. So the general rule of thumb here is if I have an area of high pressure and an area of low pressure next to it, we're always going to go from high to low. High to low is the direction the wind's going to go here. So it's that difference in air pressure, that difference in temperature, that difference in density that drives the wind. So even though in our geology and volcano units, we spoke about convection in a liquid, this in a sense is a convection in a gas that is actually causing wind to move. That movement of high pressure to low pressure, high temperature to low temperature. Humidity is important because it's the amount of water vapor in the atmosphere. We need to know this for a couple reasons. One, it helps us know if it's going to rain. Humidity is a very good indicator of rain, or dew point more specifically. But it also lets us know if it's kind of unsafe for us outside. Every location around the planet has a certain saturation point or the total amount of moisture or water vapor it can hold. If it's 100% humidity outside, it means the air is not able to take in any more moisture. That's why in a really humid day, if you're outside, you get sweaty, you're not able to cool down because that sweat on your body is not able to kind of evaporate into the air around you. And it's that evaporation from your skin that actually cools you down. So if the air has reached a full saturation, you're not able to evaporate your sweat off your skin, you're not able to stay cool. For meteorology standpoints, if the air is very saturated, a lot of moisture in the air, that's probably when you get those random pop-up thunderstorms around 4 p.m. in like July and August in the summertime months. So humidity, the amount of water vapor in our atmosphere. Now we have a couple points that go along with humidity. We have relative humidity, that's the amount of water vapor in the air compared to its saturation point. We're going to do a whole lab on relative humidity. Dew point is the temperature at which water vapor turns to water, rain. So when the dew point equals the air temperature, your relative humidity is at 100%. So sometimes the dew point will be 65. When the dew point and air temperature reach the same point, it's probably raining outside. Latent heat, this is the difference in thermal energy when comparing water vapor to liquid water. So the importance of latent heat really just has to come down to like condensation, how water forms, how that releases heat, and then that heat provides energy to form a storm. So latent heat, you want to think of latent heat kind of as almost like the fuel that's used to create like a thunderstorm or something like that. So all of these mean something slightly different, and it's going to be really good that you kind of are able to kind of differentiate the process. Another one is called adiabatic process. That's a hard word for me to to pronounce. Adiabatic process. Its temperature changes without the addition or removal of thermal energy. Temperature changes without energy, and this has to specifically do with pressure. Adiabatic heating is as pressure increases, the molecules are forced together to create heat. Adiabatic cooling, when pressure decreases, molecules move away and cool down. You can actually use an adiabatic process to boil water at a lower temperature than 210 degrees Fahrenheit or 100 degrees Celsius. Because if you just increase the pressure, you don't need to make it as hot to get water to boil. You can do some fun experiments and things like that. If we have time in class, I'll show you one experiment where you can actually boil water using ice. It's pretty cool. This is a chart that just kind of shows the same thing about our adiabatic heating and stuff like that. So here's some more information about different things associated with adiabatic heating, like dry adiabatic lapse rate, moist adiabatic lapse rate. We don't have to worry so much about those two. Lifted condensation level. This one's kind of important that this is the height in the atmosphere in which condensation happens, where clouds can form. So LCL, or lifted condensation level, this is the point in our atmosphere, in the troposphere, where we're going to have condensation. You might ask yourself, is this always going to be the same level? No, it comes into play with all these different atmospheric conditions that we've been talking about already. So the LCL is not going to be one constant height. Why isn't going to be kind of, the same height? Well, pressure and temperature, they're always changing as altitude changes. And our pressure and temperature kind of control everything else that's going on within the atmosphere. So it's important that we kind of are able to evaluate the different atmospheric properties at different levels in the atmosphere. When we go to forecasting, we'll look at different weather maps that show how these properties kind of look and appear at different levels in the troposphere. But for now, just understand that why atmospheric properties change in altitude, pressure and temperature are controlling everything, and it has a very large effect. So that's going to end our properties of the atmosphere section. I know there's a lot in here, so it might warrant you to go back, rewatch. If you have any questions for me, please go ahead and ask. If not, have a good rest of your day, and we'll see you in the next video where we'll be focusing on clouds and precipitation. Bye-bye.